Hello everyone, this is Nashrah Afroze. I'm a PhD student at Georgia Tech, and today I will be talking about how we can improve the endurance of ferroelectric capacitors at higher temperatures, and we'll introduce the term self-healing ferroelectric capacitors. There has been a lot of research going on for improving the reliability of ferroelectric memories at room temperature, but I will be talking about why making ferroelectric memories reliable at elevated temperature is important and how we can achieve that. This is a collaborative work among Georgia Tech, Unimore, UNIST, and Applied Materials. Latest trend in the semiconductor industry is the 3D integration of memory on logic. But we still have a significant challenge over there, which is thermal management. Because depending on the chip activity, when the front end CPU or GPU gets heated, that heat gets transmitted to the back end of the line memory stacks as well. So if we want to use ferroelectric memories for memory on logic applications, they must be reliable at higher temperatures. For example, uh, according to JEDEC standard, the BOL memories need to qualify at 125 degrees Celsius. However, we know that ferroelectric memories suffer from reliability issues and it gets even worse at higher temperatures. So ferroelectric memories fail very quickly when we go to higher operating temperatures as shown by the blue curve here. But this is not something desirable for memory and logic applications. For memory and logic applications, we want memories to be reliable for a wide range of temperature, from room to the elevated levels, like as you can see here in the red curve. So in this work, we will be presenting a temperature activated self-healing process by inserting an oxygen reservoir layer to improve the endurance of ferroelectric capacitors at higher temperatures. And for this study, we have compared this set of device that you can see here in this slide. So one is the reference device and another is the oxygen reservoir layer device, or the ORL device, which has the tungsten oxide layer at the bottom interface, which will act as oxygen reservoir here. The corresponding PV loops measured at the pristine state at 25 degrees Celsius are shown at the bottom for each device. So let me briefly describe how we have fabricated these devices. So the fabrication process for the reference and ORL device are pretty similar. So we first sputter 20 nanometer tungsten bottom electrode, and for the ORL device we do one extra step, which is we use oxygen plasma in the ALD chamber to oxidize some portion of this tungsten electrode to form the tungsten oxide layer, which will act as the oxygen reservoir layer here. Next, without breaking the vacuum for the ORL device, we deposit 5 nanometer HZO on top of it using thermal ALD process. And in case of reference device, we deposit this layer right after sputtering the tungsten electrode. Next, we sputter tungsten again of 70 nanometers thickness for the top electrode, and you can see the corresponding PV loops at the bottom. We did the TM imaging of both the devices. So you can see here in the ORL device, or the oxygen reservoir layer device, we can clearly see the presence of tungsten oxide, which is absent in the reference device. Going forward in my talk, I will be referring to this device, which has oxygen reservoir layer or tungsten oxide, as the ORL device. We further did EDS scan on this ORL device. And from the material count coming from the tungsten and oxygen here, you can see that one tungsten oxide layer is actually getting formed at the bottom interface. And this is clear from the line scan on the right as well. Next, we did material characterization of this layer to find the stoichiometry of the tungsten oxide. So with the help of TM imaging, we could see that this tungsten oxide is monoclinic in phase. And we performed XPS on this tungsten oxide layer and found that this is actually WO3 with 28% of oxygen vacancy, meaning this is a substoichiometric tungsten oxide layer. We did GI XRD scan on the HZO film of both the reference and the ORL device, and we could see that both the films have comparable amount of orthorhombic phase fraction in them, which means that we are not losing any ferroelectric properties due to having the tungsten oxide layer in the ORL device. And this could be clear from the electrical pond measurement shown on the right. So the black curve is coming from the reference device and the red one is coming from the ORL device. So we have applied different voltages and used 200 nanosecond pulses to switch the polarization. So as you can see here that both the devices has very similar saturated polarization and also very similar coercive voltage. And I would like to mention here is that both the devices show 100% switching at 1.8 volts. So this is the pulse scheme that we have used for measuring the endurance of both the devices. We have used bipolar cycling pulses of 200 nanosecond each and have performed consecutive read operations to measure the 2PR values after a certain number of cycles. And using this pulse scheme, we measured the endurance of the ORL device which has tungsten oxide, and we could see that this device didn't break at 10 to the power 12. So we could only see this data, but we wanted to show you a distribution across different devices of both the samples. So here you can see the top plot is coming from the reference device and the bottom plot is coming from the ORL device. And in each case, we have measured 3 to 4 devices. And on average, we could see that the ORL device is surviving longer or having higher endurance compared to the reference device. So these measurements were done at 25 degrees Celsius for 1.8 volt of fatigue pulses. Next, we did the same measurement at 85 degrees Celsius, 105 degrees Celsius, and 125 degrees Celsius. And we could see that in each cases, the ORL device has higher endurance compared to the reference device. To summarize these data, I have plotted it in a different way. So here you can see the x-axis is temperature and the y-axis is cycles to breakdown or the endurance of this device. So for the reference device, you can see that as we are increasing the temperature, the endurance degrades very fast for this reference device. However, in case of the tungsten oxide device or the ORL device, we can clearly see that we're having higher endurance at each temperature due to the presence of this tungsten oxide layer, and this endurance enhancement is up to 3 orders of magnitude at 125 degrees Celsius. So due to having tungsten oxide, we are having higher endurance at all temperatures. Next, we feed the cycles to breakdown versus temperature data into Arrhenius model to get the effective activation energy. So the smaller the activation energy is, the smaller is the temperature dependent breakdown of the device. So we plotted inverse cycles to breakdown with respect to 1 by kT, and the slope of the fitted line is the effective activation energy. You can see that the activation energy of ORL device is smaller compared to the reference device, which means the temperature dependent breakdown has been suppressed in the ORL device due to the presence of tungsten oxide. Next, we measured the endurance at multiple voltages as well. For example, you can see the top panel is coming from the measurements done at 1.6 volt fatigue cycling, and the bottom panel is coming from the measurement done at 2 volt fatigue cyclings at different temperatures. So in all cases, you can see that the red curve or the measurements done on ORL device has higher endurance compared to the reference device. And we have measured multiple devices for each voltage and each temperature. So if I have to summarize the full endurance data, then this is how it would look like. So here, x-axis is the voltage that we have applied for bipolar cycling, and y-axis is the cycles to breakdown or the endurance. So you can see that at 25 degrees Celsius, the ORL device is having higher endurance compared to the reference one. And this difference is even higher at 85 and 125 degrees So the endurance of ORL device is much higher compared to the reference device at 85 and 125 degrees Celsius. So next we wanted to know and understand that where this endurance enhancement is coming from and if trap generation rate is playing a role here. So for that study, we have measured the leakage current for both the devices. So you can see the top plot is coming from the reference device and the bottom plot is coming from the tungsten oxide or the ORL device. Each plot has multiple curves here. So these are coming from the measurements done at 25, 85 and 145 degrees Celsius. And these plots are coming from the pristine device and we did the same measurements after 10 to the power 3 and after 10 to the power 6 cycles. Next, we use Nashrah to fit this leakage data. Nashrah is a commercial device simulation software from Applied Materials which can describe carrier defect interactions in the devices. So we use that software to fit the leakage data for both the devices. So you can see here that the circles are coming from the experimental data and the solid lines are the fitted data using Nashrah. So after fitting this data, we could find the band diagram for both the devices. So there is a lot of detail going on here, but what I would like to talk about is this slide. So here you can see in the band diagram of the tungsten oxide layer that the dielectric constant of the tungsten oxide is 87. And another interesting thing here is that um, although we have asymmetric device structure for our ORL device, meaning we're having tungsten oxide only at the bottom but not at the top, but still the IV characteristics is pretty symmetrical for this device. And this is happening due to the band alignment between tungsten and the tungsten oxide layer. So you can see here that the electron affinity of tungsten oxide is getting aligned with the work function of the bottom electrode, for which we are getting symmetric IV characteristics for this ORL device. Next, we wanted to study or find out the trap generation rate for both the devices. So for that, we have plotted the leakage at 1 volt across different number of cycles for both the devices. So the middle plot is coming from the reference device and the right plot is coming from the ORL device which has tungsten oxide. And each plot has multiple curves which are coming from measurements done from 25 to 145 degrees Celsius. And the leakage at pristine state, we will be denoting it as J naught for the future studies that I will be showing. And the leakage after a couple of cycles, we will call it as Jn. So here you can see that this is a plot where the y-axis is del J over J naught and x-axis is the number of cycles. So del J over J naught is the difference between the leakage coming from certain number of cycles and the pristine leakage and divided by the pristine leakage. So this is basically the slope of this plot is basically a measure of trap generation rate. So the black curve is coming from the reference device and the red curve is coming from the ORL device. And this is for the measurement done at 25 degrees Celsius. So you can see the slope over here is very similar for both the devices. But as soon as we are going to higher temperature, say for 85C, the slope of the reference device increases compared to the ORL device, which tells us that the trap generation rate increases in the reference device at higher temperature, and this is true for 125 degrees Celsius as well. So we again use Nashrah to find the relative trap density for both the devices, and we could see that with cycling the relative trap density in the reference device increases, whereas in the ORL device it's getting suppressed with cycling. So here we could clearly understand that due to the presence of tungsten oxide layer, the trap generation with cycling is getting suppressed, for which we are getting improved endurance in these devices. Now that you have seen all the experimental results. Let's take a step back and think why trap generation rate is getting suppressed at elevated temperatures. To find that, we have carried out DFT calculation, and we have used the following atomic structure for the calculation. So here you can see that on the top we have orthorhombic hafnia, and at the bottom we have monoclinic tungsten oxide layer. Next, we have deliberately created some vacancies at the hafnium oxide layer, which is vacancy number 1 and 2, and we have calculated the vacancy formation energy for these positions. Next, we did the same. We created vacancies at tungsten oxide layer and calculated the formation energy for those vacancies. So here you can see that the vacancy formation energy for tungsten oxide is smaller compared to that of hafnium oxide, meaning it's easier to form vacancies in the tungsten oxide layer compared to hafnia layer. Now, why is this important? This is important because it means tungsten oxide can generate more oxygen ions, for which it can act as oxygen reservoir layer. Next, we wanted to see how much energy is needed when these vacancies migrate from one layer to another. So first we have calculated the migration energy of oxygen vacancies when it moves from hafnia to tungsten oxide layer. And for that it needs energy of around 2 electron volt. But when oxygens from tungsten oxide would migrate to hafnia, it would need energy of around 4 electron volts, meaning vacancies will need higher energy for going from tungsten oxide to hafnia layer. So we are clearly seeing an asymmetric behavior in the vacancy migration, or asymmetric barrier for vacancy migration across this HZO tungsten oxide interface. Now, why this asymmetric barrier is so important? Let me try to explain this in terms of oxygen migration. Say we have HZO on top and tungsten oxide at the bottom. As we keep cycling the device, we keep generating more and more oxygen vacancies in the HZO film, and this phenomena is even worse at higher temperature, for which the device breaks early. So let's see what's the role of tungsten oxide here. When we are applying positive voltage during bipolar cycling, the oxygen from tungsten oxide would want to go to HZO. Say this oxygen wants to go to HZO and recombine. If it does that, it will need an energy of 1.8 electron volt. But during the negative voltage application during the cycling, the oxygen would want to go back to tungsten oxide from HZO and recombine, for which it will need energy of 4 electron volts. So here we can clearly see that it's easier for oxygen to go from tungsten oxide to HZO, and due to the higher barrier height, it's unlikely for oxygen to come back to tungsten oxide. Staying in HZO, what does the oxygens do? It recombines with the vacancies that are generated in HZO with cycling at elevated temperature, partially heals those vacancies, delays the breakdown, for which we are getting higher endurance in the devices with tungsten oxide layer. And this is the reason why we are calling it as self-healing capacitors. We have tried to compare our devices with some of the recently published ferroelectric capacitor results. So here you can see that we have applied sufficiently larger electric field in our measurements just to confirm that we are doing full switching. Although I have discussed extensively about the endurance of the ORL device, but it has some good behaviors as well. For example, it doesn't have any wake up, and in pristine state, it is having pretty decent 2PR value, which is 38.8 microcoulomb per centimeter square. And as I have mentioned that we are getting comparable endurance at room temperature, and we are getting highest endurance at 125 degrees Celsius for full switching when we're comparing it. We're comparing our ORL device with some of the recently published data of ferroelectric capacitors. So in conclusion, we can say that due to the presence of tungsten oxide layer in the ORL device, we are getting improved endurance up to 3 orders of magnitude at 125 degrees Celsius, and we are able to suppress the temperature accelerated breakdown in this device. This is happening because the trap generation rate at high temperature is getting suppressed in the ORL device, and this is possible due to the asymmetric barrier height for vacancy migration, which is actually enabling the self-healing process, which is the key mechanism behind the endurance enhancement at elevated temperatures. I would like to thank all our sponsors. With that, I would like to conclude my talk. Thank you.